So we're continuing to talk about exponential models. Exponential models, also known by the name log linear models, will somehow become Max-Ent models, which is what everybody wants to know about. But I prefer to call them exponential models because of how we derive them here. I'm going to show later on, probably today, how you can derive the same models from a maximum entropy principle point of view. So we'll discuss both. What we said was that we have a problem of many different knowledge sources that we're trying to combine to make a joint combined prediction, and that the straightforward, simple way of doing that using a decision tree leads to too much fragmentation in the data, rapid fragmentation, and we were looking for something that would not lead to fragmentation. So one solution we proposed was build a separate prediction from each one of these knowledge sources and then combine them linearly by linear interpolation. The advantage of that is that it's very simple and very easy to build these individual, independent, separate predictors. And it's very easy to combine them with weights. You know that any weights that you choose, as long as the weights sum to 1, what you get is a bona fide probability distribution. You don't have to worry about normalizing it. And we also have a very good method for choosing those weights based on held out data. This is what we call the degenerate EM that you've implemented. On the downside, I try to argue, and at that point I fell into a lot of hand waving, that it's usually not the right way to combine information sources or to combine different predictors, at least in the context of language. And I gave the example from if you're trying to combine syntactic information with long-distance semantic information. If the syntactic information is very strong, like you really can't have a noun here, it doesn't matter that you're in a document that deals with financial instruments or financial issues. You don't want the word bank here. So I suggested that instead of thinking about it as two independent contributions to the prediction of the word bank, we think about it as each knowledge source provides some modification to an existing estimate. These modifications are in the form of increase your current estimate by some factor or decrease it by some factor. I call these bumping factors. And that led to a model that looks like this. Looks like some product of bumping factors that multiply something else that comes here. And these bumping factors will be present or not present depending on whether they apply to your current situation. So one way of expressing it in the formula is to raise this mu to the power of an appropriate function, call it fi, which is a function of both of the history and the word. And in the simplest case, this function, which we call the feature function, is an indicator function. It's either 0 or 1. It's typically 0 most of the time, and it's 1 when the particular condition to which you want to apply the bumping factor occurs. I then said that instead of looking at the probability, I can also look at the log probability. When this product becomes a sum of things like this, lambda I, fi of hw. And this is sort of trivially true if lambda I is defined as the log of the mu I. If we want to keep looking at the probability rather than the log probability and still express it in terms of the lambdas, this becomes e to the power of sum of lambda I fi hw. You're going to see all of these forms. the log probability has this main component, which is a linear combination, which is why it's called log linear. Namely, the log of the probability can be expressed as a linear combination of feature functions. Or the original probability can be expressed as e to the power of a linear combination. If you identify e to the lambda I with mu I, these are identical. I deliberately left space here because there's something that you start with. And we got into a little bit of confusion or trouble last time when I claimed that what you start with is the sort of the default, or that was due to my hand waving. In the most general case, I can just start with, I want to make sure that for any h, this is a real probability distribution, so that when I sum over w, it sums to 1. So I will put here a normalizing factor that depends only on h. I'll put it here too. Where z of h is defined as, by construction, if I want this to normalize to 1, this will be defined as the sum of this part over all words in the vocabulary. I goes from 1 to n, lambda I, fi. So I can, in principle, calculate the normalizing constant for any given history by summing over the non-normalized part for all words in the vocabulary. The vocabulary has, say, 100,000 words. It's a long loop, but it's not undoable. So calculating the normalizing constant is doable, but maybe computationally demanding, somewhat demanding. In the log domain, it would look like log minus log of z of h. Minus because z is in the denominator. So this is my exponential model. And it has parameters lambda. Lambda goes from 1 to n for my n sources of information or n features. You will also see it written sometimes in shorthand as e to the lambda dot f. So think of the lambda as a vector of n numbers, and the f as a vector of n feature functions, or equivalently of the specific values of the feature functions for specific h and w. And the dot here is the dot product. Multiplication of two vectors of the same length by multiplying them element-wise and summing together. So you might see this form in many places. To remind you, the lambdas could be either negative or positive, or 0. And that corresponds to mu's that are either greater than 1 or smaller than 1, or 1. So when the lambda is positive, mu is greater than 1. When lambda is negative, mu is less than 1. The mu's are the bumping factors, by how much you're going to change your probability estimate by considering the current feature, by taking into account the fact that this current feature is valid. Sometimes it will cause you to increase your estimate, sometimes it will cause you to decrease it. My next question is, how do I fit the value of these parameters from data? So given a set of features, features are different aspects of the data that we care about. So these are FIs. So they're functions. They're functions of the data. And given training data, training data can consist of a single long training set document, but I always like to view it as a set of pairs of H and W, right? We discussed it before. So it would be H1W1, H2W2, all the way to Hn. We used N here, so it'll be big N. H big N, W big N. So W is small, big N. Where the H1 is the history before the first word, so it's the null history. H2 is the history all the way up to but not including the second word and so forth. It's that window. And you can decide that the history gets flushed at the end of every sentence or at the end of every paragraph or document or what have you. But in general terms, we deal with a set of pairs, a set of ordered pairs. Now my question is, how do I estimate lambdas? The only parameters I have are lambdas. Once I decide on the set of lambdas, the normalizing constant is automatically determined for me. I don't have control over it. It has to be the right normalizing constant. You should notice that z depends not only on h, but also on the lambdas. So I can sometimes write z with a subscript of lambda. So z is a function of the history, but it's also a function of the parameters. You can write it here as well, and here, and here. So now my question is, how do I choose lambdas? Any suggestions? How do you usually go about estimating parameters?
Minimizing the average log likelihood of complexity on the handout data set.
Maximizing. Perplexity, maximizing log likelihood.
Yes.
Okay. But this is how you, well, you're right. I use lambda, and I used lambda in the past for deciding the interpolation weights. And in that case, I had original training data. I trained my individual components, and then I had a held out data for training the interpolation weights. You're right. In this case, I don't have an original, anything that happened before this. This is my training. So the answer is effectively what you said, but I don't call it held out data. It is my training data, and I'm going to train it using the maximum likelihood principle. I'm going to look for the set of lambdas that maximize the likelihood of my training data. MLE, or ML, is the argmax over all possible sets of lambdas. Lambdas, by the way, come from r to the n. Every lambda could be any real number. Of the likelihood of my data given the parameters. Let me write that likelihood explicitly. It is the sum over all history and word in my training data. So I sum over all these pairs of the likelihood assigned by the model. So it's 1 over z of h under this given lambda, e to the sum of lambda I fi of h and w. That goes from 1 to n. Now lambda features here in two places. One is here, and the other one is here. In principle, I'm now searching the space of all possible lambdas, which is a search in a high-dimensional Cartesian space, for something that maximizes this. Argmax, yeah, of course. This is not log likelihood. This is likelihood. Argmax of the product. I goes from, thank you. Oh, there's no I. well, you can say h of wi, h and w number I goes from 1 to n. You can do it that way. Thank you. The good news is that this function is convex in the lambdas. Haley?
There's no difference between uppercase and lowercase n here, is there?
There should be. So I use, thank you. This is n, this is small n. So I use small n for the number of features and big N for the items in my training data. Thank you. If I make a mistake anywhere else, please correct me. So here is I goes from 1 to n, and here index goes to n to begin. The good news is that the function, this function, the likelihood function or the log likelihood function, are convex. That means there is one solution that will have the maximum value, and it's not hard in principle to find it. You could use gradient descent if you want it. I'm going to give you a different algorithm that has more of a flavor of the EM algorithm. It's not quite EM, but it's an iterative reestimation algorithm. And as a result, it behaves more like EM than gradient descent in that it doesn't take many iterations to converge. You can start anywhere you want because it's a convex space, and you will always end up in the same place. Here's how the algorithm works. Step number 1 is initiate the lambdas. So as usual, I will use the superscript of 0 to indicate the values of the lambdas you start with. Step number 2 is you calculate for every I, for every feature, I goes from 1 to small n, the expected value of the feature under the current model. I will write that as expected value under the current model. This is the current model, so this is model L, right? We use L for the current, of Fi. The expected value of the feature function on the empirical distribution. So let me write it in an equation, and then maybe I'll have an easier to understand.
They're independent of the weight, right? They're binary flags.
They don't have to be binary, by the way, but it's easier for us to think about an example as binary. They could be multi-valued. They could be even continuous valued.
Sure, but they still don't depend on their weights, right?
They don't, in the sense that you first define the features, and the features functions remain fixed during this training process. The only thing that changes are the lambdas.
But I don't see how the expected value of a particular function
Ah.
depends on the weight.
Okay, so let me write the expression, then I'll interpret it for you. We will sum over all the histories that we've seen in the training data. So this is summation order n. And then for each one of them, we will sum over all the words in the vocabulary. And we will weight by what the model, the current model, according to iteration L, thinks of the current word in the current context. And then multiply it here by Fi. So this answers your question. the dependence on lambda is through this dependence on this weight. So how do I interpret this? One way to write this, first of all, the summation of the training data can be written slightly differently, can be written as summation over all possible histories multiplied by the empirical distribution of the history. P twiddle is usually used to mean empirical distribution. Empirical distribution is that distribution of the data itself. And empirical distribution, the empirical distribution of the history is the number of times this particular history occurred over the number of histories overall. It's that very silly distribution that is 0 for most histories and 1 over n for the majority of the remaining, and maybe 2 over n or 3 over n for some of the others. It's the non-smooth relative frequency in the training data. I'm adding it here just because in some texts you will see it this way. You can either sum explicitly over all the histories, or you can sum, over all the histories that were seen, or you can sum over all possible histories weighed by how often they were seen. There's a factor of 1 over n here, which, like 1 over n here. One of them is summation by token, the other one is summation by type. Which one is summation by token? Which one goes over one token at a time? The top one. The training set is a set consisting of many tokens, n tokens. This is summation by types. This sums over all possible history types, weighs each one by how often it occurred. That's just a side note that there are two different notations. You'll see them both. But what do I make of this thing? Let me go back to the initial step and add something I forgot to add, which is calculate the empirical distribution of each feature. The empirical expectation of each feature under, the expectation of each feature under the empirical distribution. What is the empirical distribution of H and W? It's basically how many times H and W occurred over the size of my corpus. So again, for most H and W combinations, it'll be 0. For a few of them, it'll be 1. And for even fewer than that, it'll be larger than 1. This is the expected value of the feature function under the empirical distribution. This is the expected value of the feature function under my current model. How do I calculate this? This is very, very easy. It is just the frequency with which this feature was on in my training data, if it's a binary feature. Or even if it's not a binary feature, the formula I will write will be equally good. For all H and W in the training data. Or I can equivalently write it as sum over all H and W, all possible H and W, which is a huge space, but I multiply here by the empirical distribution of H and W. I multiply by Fi of H and W. These two are the same things. This is summation by type. This is summation by token. This is going to be 0 over n or 1 over n for most cases. So I forgot to do this before. This is done once. Because it does not depend on my current model, it does not need to be updated. So my initialization step is to choose some initial parameters and therefore define my initial, my 0 iteration model, and on the side to calculate the empirical prevalence and the empirical expectation of the FIs. If the FIs are binary, this basically means their prevalence. How often are they on? If they have multiple values, it's more general, their mean value, their expected value. Now back to my iterative step. Now for a given model of iteration L, I calculate the expectation of the feature under that model. Now it's kind of a hybrid. This part is under the model, but this part is actually going over the empirical distribution of the history. Right? I broke here. It was very clear that everything was according to the empirical distribution of the history and word pairs, the conditioning event and the predicted event. Here, the conditioning event behaves according to my training data. The predicted event is weighed by what my model assigns it. My goal is to find lambdas that make this equal to this. Goal, find lambda such that the expected value of the feature according to my model with this lambda is equal to the expected value of the feature under the empirical distribution. And therefore, my update rule is going to be lambda I, and I want this to be true for all I. For all I goes from 1 to n. My update rule is going to be lambda I of iteration L plus 1 is going to be defined as lambda I of iteration L plus a correction factor that will depend on the discrepancy between these two. And the specific dependence is going to be through log of, if this is bigger, I want to increase it, so it's E p twiddle of Fi over E p lambda of Fi. So if I reach the situation for any one of the i's where the model I have in my hand, this is P gamma L of the current iteration. If I reach the situation where my current, where the expectation of the feature I under the current model is the same as its empirical expectation, as its target value, this over this will be 1, log of 1 would be 0, and I will add 0. In other words, I will not change my lambda. If, however, my current expectation, the expectation according to the current model of iteration L, for feature I is too low relative to the target value, then this over this will be a positive number. Log of a positive number, I'm sorry, this over this would be larger than 1. Log of a larger than number is a positive number. I will add a positive quantity to the lambda for my current feature. And as a result, I will increase the bumping factor for the situations when that feature is active. So that when I go back and recalculate the expectation, when this feature is active, the model would assign that particular W a higher value, and therefore the expected value overall will tend to come to this. So I can call this step 3, and then my iteration, my iterative process is going between 2 and 3, 2 and 3, 2 and 3, until these conditions are matched. Will they ever match? The answer is yes. I will eventually converge. I'm guaranteed to converge the way I derived my target values, I'm guaranteed to converge to a set of lambdas, to a unique set of lambdas, where this will become equal to this, where this is equal for all i's. I don't have a good guarantee on how long it'll take to get there. So theoretically, it could take a very long time, an exponential amount of time. In practice, it doesn't. We converge very fast. In fact, much faster than the number of iterations you need for a gradient descent, for example. It's somewhat comparable to EM in that, you know, depending on the situation, it could be 5, 10 iterations, 100 iterations. We do tend to converge. All the lambdas are changed in parallel. So there will be my initial set of lambdas, and they would lead to the next set of lambdas, and that would lead to the next set, etc. And then we're going to guarantee to converge. Is this computationally expensive? The answer is usually yes. The number of iterations here is not a problem. In practice, it would be on the order of 10, maybe 100. The hard part, this is clearly not hard. Once you've calculated this, this is fixed, doesn't change. You calculate it once. This you calculate for every iteration. Just comparing the two and doing it for as many, this is for any I. How many features are there? Could be 100,000, could be 1,000,000, but that's not a big deal. The big deal is this. Computationally demanding. And why is this a big deal? Because A, you have to do it for every feature, so that's n features. B, you have to go over all the training data, all histories that occur in training data, so that's big N. C, you have to go over all the words, so that's V. And D is that hidden inside here, you need to calculate the normalization factor, Z of H and W. Now, you don't have to recalculate it for each one of these. You have to calculate it once for each history. So it's this plus number of histories times whatever it cost you to calculate this. And if you remember what it cost you to calculate this explicitly, we have it here, is a loop over the vocabulary, and here an inside loop over the features. So it's another V and N. So I guess these are comparable. But this could be very large. So number of features could be 10 to the 6. Vocabulary could be 10 to the 5. And size of training data could be 10 to the 8, 10 to the 9. Put them together, and pretty soon you're talking real money. So there have been a variety of shortcuts suggested over the years. If you build your data structures right, there are things you don't have to recalculate, but it's a struggle. In general, training an exponential model is computationally challenging. Not to say impossible, but challenging. The beauty of it is that using it is nowhere near as expensive as training it. That's true for many models, because you don't need to recalculate the normalization constant. It satisfies the condition that we wanted, which is each feature contributes in a way that is somewhat independent of the other features. Now, it doesn't mean that the features are independent. The features need not be independent. But their dependence and their interaction with each other is figured in during this training process, so that the lambda that each feature gets already takes into account the context of the other features that are active in the model. One second. Let's take an extreme example. Suppose you incorporated two features that, unbeknownst to you, were highly correlated. Let's take even the most extreme example. They had a correlation of 1. You, by mistake, included the same feature twice, gave it two different names, but it was the same feature, so you give it the same information. Or perhaps one feature was a complement of the other feature, so again, they had a correlation of 1. What would happen in this case is if you included only one feature, one of the features, f1, you would have gotten some lambda 1. But if you include both f1 and f2, well, I'll call it fa. Okay. Lambda a, fine. If you include fa and fb, you would get a lambda a and a lambda b that would be less than the lambda a, and in fact the sum of them together would be equal to the lambda a here. Why the sum? Because if you look at the form of the model, if instead of one feature here you threw two that had exact same values, fa and fb, they would be prefixed by a lambda a and a lambda b, so they will do the exact same job as a single feature that had a prefix that was the sum of the two. Now, why do I not say that the two lambdas would be each would be half of this? Is because they don't have to be half. There is some redundancy in the model if there are two features that are exactly the same. If two features, a and b, are identical, they're the same feature, they're the same function, then the model would give the exact same output, exact same values, if lambda a was 3 and the lambda b was 2, or if lambda a was 4 and lambda b was 1, or if lambda a was 4.5 and lambda b was 0.5, or if lambda a was 5 and lambda b was 0, or even if lambda a was 6 and lambda b was -1. In other words, as long as the sum of these two is the same, effectively it'll be the same model. So if you include multiple redundant features, there is redundancy in the model to the point of what statisticians call non-identifiability. Namely, there is no way of distinguishing these models from each other because they give identical likelihoods to the same data. In the more likely case, where you include features that are not identical, but are still highly dependent, highly correlated, this iterative procedure will work out the mass distribution between the lambdas such that the model that you get at the end will take into account the fact that some features tend to affect or interact with many other features, so all the lambdas that are affiliated with that will go down. So back to the first assertion from which I started this, we're not assuming here that the features are independent. This is important. Features may not be independent. But what we do have at the end is a model where each feature has its own bump, and the bumps are applied independently. So any feature, let's say a feature that says that in the context of a financial document the word bank should be bumped up by a certain amount, 3.5, that feature always applies the same bump whenever it's appropriate, regardless of whatever other features are present at the time. First, a general answer. Compare this model, this way of combining data, to the linear interpolation way of combining data. This model usually does much better. Now, addressing overfitting. Overfitting in this context happens when you use many more features than can be justified by the amount of data you have, and you demand that the model would satisfy all of them. I would say that if the features are appropriately represented in your data, it should not lead to overfitting. So if you require that every feature, let's say these are binary features, and every feature that you include must have occurred in your training data at least 30 times out of as big an N as you want. But 30 times means that the binomial estimation, is reasonable. Then I would hazard to say that you will not have overfitting regardless of how many features you have. The problem is that that's not usually the case. Often you are interested in many, many features which are very rare, and it happened very rarely. Let's say a feature happened exactly once. Let's start with the even more extreme case. Suppose the feature never happened. If a feature never happened, the only way the model would be able to create a zero expectation, because the target empirical expectation would be 0, the only way the model will create zero expectation is by taking the lambda associated with that feature and driving it to negative infinity. Right? When that lambda is negative infinity, e to the negative infinity becomes 0. And you will see it in practice. If you try to train features and you look at the iterations and you see that some of the lambdas are drawn to either positive infinity or negative infinity, you should realize that you're trying to train on features that drive some part of the event space to 0. Let's take a less extreme case. Suppose your feature occurred in your training data exactly once out of 10 million. It's probably not a good idea to force your model to assign a probability of exactly 1 over a million or 10 million. But if you did that, you'll be driving the exponential model towards the empirical distribution. I mentioned that this will always converge. It will always give you an answer. Whatever the features are, it will converge. The caveat is if the features have expectation 0, it will converge with some lambdas that go to negative infinity. But if all the features have expectation non-zero, it will converge to a real model. But that real model is not necessarily a good one. It'll be an overfitting model. It will tend towards the empirical distribution. I hope you realize that the empirical distribution is not a good distribution. It's an overfit. It's the ultimate in overfitting, right? Because it's claiming, it's pretending that the entire world consists only of what I've seen so far.
Yeah, so it would have been doubly awkward.
I can capture my standard models like n-grams in this exponential framework. Let me go over examples of how I do that. Suppose I want to capture just a unigram capturing a unigram in an exponential model. I will do that by coming up with one feature for every word in the vocabulary. I will do that by throw into the mix exactly V unigram features. Each one of them, I will index it not by I, but by the word in the vocabulary that it covers. For every word in the vocabulary, F sub W, it's always a function of the history on the word, would be 1 I use the same thing here. I call it WJ. And I'll say here for J goes from 1 to V. So this is a set of V features, one for every word in the vocabulary. And a particular feature, FWJ, or I'll call it F the. So I've now indexed it by words in the vocabulary. Is going to be 1 if and only if the word in its argument is the. And it's 0 otherwise. Extremely degenerate feature. It ignores the history and only looks at the word. Not surprising, because the unigram ignores the history and only looks at the word, right? And now my target values the expectation under the empirical distribution of the feature F the is, I can use either this form or this form. It's important for you to really know why these are the same. This happens a lot in derivation. Sometimes you see this form, sometimes you see that form. Question?
One question here. I'm slightly confused. These two forms, in one of the forms we have 1 by n, and in the second form we have sum over the probability distribution.
Right.
I didn't see the summation over p should give us 1 by n outside.
Summation over p. So remember that p twiddle consists of values that are either 0 or 1 over n, or sometimes it will be 2 over n. I'm sorry?
You have it listed as the count of the history of the word.
It's count by n, so it's just c by n.
Yeah. It's the count. It is the count, but the count would typically be either 0 or 1 or 2. So let's go over that in greater detail. What should I erase? I want to show you that summation 1 over n, summation over history and word in the training data of anything that depends on them, on some function g of h and w, is the same as summation over all possible history and words of the empirical distribution of h and w times that g of h and w. This g is not important at all. The only thing that's important is this part. P twiddle of h and w is how many times h and w occurred in the training data, divided by how many training elements there were. So far I'm just copying what I did before. You still have difficulty with that? Okay. Is it clear? It's all right. Let me think of an example. Something to make it clear. Okay, I can count. I can count how many times E occurred in the corpus in 2 different ways. The letter E appeared in the book in 2 different ways. I can go word by word in the book and count how many times E occurred in that word and add up those counts. Or I can go in dictionary order and say, how many times did aardvark occur in the corpus? how many times E is in aardvark, multiply the two, and keep going that way. The first way is by token, summation by token. The second way is summation by type. When I do summation by type, I have to multiply by how many times that type occurred. That's my pit twiddle, up to the constant n. Still have a question?
So the question is what the summation bounds are.
Okay.
In this case, it's just in the training data set, like what you're saying.
That's an index from I goes from 1 to big N.
Right, and that's just in your training data, so that's by
Right.
token. That's it.
Right.
Look at every single.
Right. This is a much bigger space.
That's like every
Huge.
possible.
Yeah, that's like v to the power of 100, or however long your history is. But of course, I'm not going to do it explicitly, because for the vast majority of this space, the empirical distribution is 0. Okay, let me go back to this. How am I going to do this? I'll do 1 over n. I'll do it summation by token. 1 over n, sum of the feature f the applied to h and w, where h and w go over the entire training data. What this comes down to basically is counting how many times the occurred in the corpus, right? How many times the feature fired, and the feature only fires when the is the word in that pair. So the target here is the count of the word the divided by n. It's not surprising. So my target value is this, and I do it for every word in the vocabulary. And then I run my iterative algorithm. It so happens that because all these features are non-overlapping, I can calculate in advance without having to run the iterative procedure where they're going to end. But nonetheless, I will keep it this way. I will just run iteratively until it converges. It'll converge to some lambda indexed by the word the, and there would be lambdas for all the other features, and there would be a normalizing constant z of h that depends on h, but in this case h is non-existent, it doesn't matter, so it will not depend on anything. It'll end up being just a unigram distribution without smoothing. It'll effectively be the same. But the fact that I chose to reformulate it as an exponential model means that I can throw in other features that may overlap. So you can think about the space of all history W pairs, and these features partition it, the unigram features partition it such that every HW pair belongs to exactly one feature, in the sense that it makes one feature fire and makes all the others not fire, right? Because it only looks at the last word. So you can imagine the space being cut into partitions, mutually exclusive, complete partitions, one for every word, the, of, in, Brazil, and so forth. And whenever features have this behavior that they are mutually non-overlapping, you don't need an exponential model. But that's only my beginning. This is my first step. Now I'm going to throw other features in. Maybe I'll throw bigram features in. Let's see what a bigram feature function would look like. A bigram feature function will involve two words, a bigram. Let me index it by the two words, say A and B. It is always a function of h and w, and it's going to be 1 if and only if h ends in A and w equals B. In other words, if the bigram AB is exactly the bigram that I'm considering right now. A is the last word in the history, and B is the word to be predicted, and 0 otherwise. How many such features can there be? Well, in principle, v squared, right? Any pair of words could be used. But most bigrams do not occur in my training corpus. So if I threw them in, I will be insisting that the model assign them probability of 0, or expectation of 0. And that will drive these lambdas to negative infinity. I'm not sure I want that. That would be equivalent. I could do that, but that would be equivalent of an unsmooth bigram. Unsmooth unigram is okay. All words occur, let's say. Unsmooth bigram, not okay. So I can choose to include just some of these features. And it's up to me which ones I want to include. It doesn't hurt anything else if I included just a subset of them. I could choose to include those bigrams that occurred more than 10 times in the corpus. I could choose to include those bigrams that occurred more than once or more than 2 times. Well, there are far fewer that occurred 10 times than v squared, right? Maybe more than v, but nowhere near v squared. So I'll say include as many of those as you want. Each such feature will have a lambda associated with it. Those lambdas will need to be trained using this procedure. We can start by training the unigram features until the algorithm converges to a set of lambdas, and then throw all the bigram features in with some arbitrary initial conditions, arbitrary lambdas. The next iteration will change not only the new lambdas, but also the old ones we had, because the lambdas depend on each other. You throw in another feature, and you potentially changed many other parameters of many other features. Nonetheless, it might be useful to throw them in chunks to let the model converge and then throw some more. Or not. You can start from the beginning. Remember that this is mathematically guaranteed to converge to a single point. So it doesn't matter in what order you do it. Can you guess what the trigon feature would be? It's not hard. F of ABC is 1 if and only if history ends in A, B, and the word is C, and 0 otherwise. Again, you can choose to include any subset of all possible trigon features. You might include those that occurred enough time. You might also be a little smarter about it. You want to only include features that add real information, significant deviation from what you had before you had the feature. Sometimes, just from having the bigram information, the trigon information is pretty predictable from the bigram information. If you have A and B very common and B and C very common, then you might conclude that A, B, C, if otherwise there's no other interaction between them, you can calculate what the expected value of A, B, C would be from the fact that B tends to follow A and C tends to follow B. And then you can go and measure how often it happens in practice. And if it happens in practice more often, significantly more often, or significantly less often than you would expect just from the two-way interactions, then you throw it in. In statistical terminology, it's called looking at the phenomena I'm after is the high level, the three-way interaction between variables. That means, is there information in the three-way interaction above and beyond what I expect would happen from two-way interactions? So you can be smart about only including things that you expect to have information. In that case, these things would tend to have a large lambda value, either a large positive or a large negative. Large positive if things happen to co-occur in your data more often than you would have expected under the lower order interactions. Large negative value if things tend to happen less often than would be expected. You can think about it as the additional bumping factor. You already introduced the bumping factor for the AB and a bumping factor for the BC. Do you need to also bump things up and down for the combination of all three occurring together? Question?
If you find that it doesn't add value in either direction,
Mm-hmm.
is it okay to just leave it in and
it is definitely okay to leave it in.
Because the lambda should sort themselves out.
Yes. Yeah. You don't suffer from including too many features. That goes back to your question of overfitting. It's not the number of features you throw in. It's what target values you assign to them. If you have a feature whose empirical value is too small and therefore you're not sure what its true value should be, then maybe you shouldn't include it.
So for features that never occur in your training set,
Mm-hmm.
you would typically refrain from including them because the weights would tend to either plus or minus infinity, right?
Right.
But what happens then about smoothing? Say you have.
We'll get there. We'll get there. Yeah, you will need to do smoothing. Smoothing will be done by way of changing your target value. So think of good Turing smoothing. Something occurred in your data once out of 1,000,000 times. We've all learned that you should not estimate it as 1/1,000,000, but as less than that, based on the good Turing formula. We can apply the idea when you set the target values for that feature. If the feature was active in your data only once out of 1,000,000 possibilities, maybe the target should not be 1, it should be 0.2. That's not exactly smoothing, this is improving the estimate, the good Turing estimate, but it functions as smoothing because you're now no longer assigning 0 to the other possibility. But there are other explicit forms of smoothing. There's also another way of introducing smoothing via a prior on the lambdas. We'll discuss that as well.
But in this case, then you would want to include all your features.
Then you could include. If you smooth the targets, you could include all your features.
That leads
And increase your computation.
not only increase your computation, but you have to learn more weights for the same amount of data, which means your weights are not as reliable.
Yes, but you could say the same thing for a smooth unigram, for example. Suppose you have a unigram with very little data. If you didn't smooth it, only the word types that occurred will get a parameter. All the others get a 0, right? Now if you smooth, many more words get non-zero values. But that's not a bad thing. Okay, so back to our picture here. These were the unigram features. Now, superimposing the bigram features over them, the bigram of the would be a subset of this. Its extent, the time when it's active, would be a subset of when the is active, right? It would be here. Because every time of the is active, the is definitely active. Every time this bigram is active, this unigram is active. So you can think of the bigram features as further partitioning of the unigram space, and the trigram features as even further partitioning in there. So far, you don't need the exponential model for that, because as long as it's a straight partitioning, you can use a decision tree, you can use a standard n-gram. Partition-based models are not a problem. We started down this path of exponential models because we were interested in what happens when features are overlapping. They're not partitioned. So now let me introduce features that are active in some weird subset of this space. And they're all going to overlap each other. And that's when we're going to see the real power of exponential models. So let me introduce a long distance feature that captures the semantic coherence of a sentence. And the feature is going to be in the form of a trigger pair, what I call the trigger pair, which is a pair of words that trigger one another. Like the example I used last time, if you saw the word loan somewhere in the history of your sentence or your document, you would like to bump up the probability that the next word, the coming word, is the word bank. But now we're not talking about loan being the last word. In fact, if the last word is loan, the next word is less likely to be bank. But rather about the probability that the word loan is somewhere in the history. I will call this loan sub naught. So A sub naught means A occurred somewhere in the history. Whereas A by itself just means the word is A. And a typical trigger pair would look like this. A sub naught triggering B. And I can have many, many different trigger pairs. In principle, V squared of them. What would the feature look like? F of A sub naught to B, always a function of H and W. The feature is simply 1 if and only if A is in the history and B is the word, and 0 otherwise. Extremely simple selector features, binary features. And associated with this feature function, there will be a lambda indexed by A naught triggering B. So for every trigger type feature, there will be a trigger type lambda parameter. And now I have my overlap galore, because the long distance trigger relationship really does not fall neatly into the categories of the bigams. One of them could be true, the other not true, and vice versa. But the model is oblivious to it. It has the same form. It doesn't care if there's overlap or no overlap. You throw the features in, you start with some lambdas, you go through the iterative procedure, you're guaranteed to converge. When you converge, you have yourself a model that takes into account all of these different feature factors, all of these different bumping factors. For evaluating the probability of a particular word given a particular history, only a small set of these features would be active, typically. But you still need to work a little hard to calculate the normalizing factor z for any particular history. So evaluating this model, using it, is not as cheap as using an n-gram or a decision tree. It does take some computation, but it's not infeasible. When we meet again, we will form a different criterion for deriving a model based on features, called the maximum entropy criterion. And we will show how it is actually the dual problem of the problem we just solved, that it leads to the exact same model. Okay? Thank you.